Okay, hello. So I want to talk about a topic in Bayesian statistics today, which I think is something that can be a bit difficult to maybe get through if you're learning Bayesian statistics, because it's relatively hard to find resources on this point. So it's relatively easy to get started, to find something where you learn Bayes rule and some simple applications, and then of course further on you can find these very advanced things where you essentially need a math degree to really understand it. But the transition in between, I think, is maybe not covered enough. So we'll give that a try. Let's introduce you to the example that I want to talk about. So essentially, we start very simple. We say, okay, we have a drug, and this drug has a binary outcome. So either the patient gets healed or the patient doesn't get healed or remains sick. And then we want to find out, okay, what is this underlying parameter? So essentially this underlying probability of getting healed. And we want to get somewhere where we have a model where we say, okay, so there is this underlying probability of the drug to work, but then we further want to say within all of our patients, there are actually subgroups. For example, we can think they have a different allele of a certain gene. So let's say they have allele A1 versus allele A2 for a gene A, and this modulates the way the effectiveness of this drug. So even so, there's this general underlying probability that also these parameters for the individual groups comes from. These probabilities get modulated by the genetic setup. So we have subgroups within a larger population. So let's get started with something that I expect you to know already. So we don't think about this subgrouping yet, but just go through this example, without any particular difficulties added. Maybe let's remain here quickly. So our observations is essentially this binary observation, right? Either you remain sick or you get healed by this drug. So this is a process that we can describe by a binomial distribution. You probably know the binomial distribution very well in terms of the context. We have a certain probabilities, like the probability of rolling a 6 on a die, and then you ask, okay, what's the probability out of, let's say, 10 rolls to get 3 times a 6 or so on. So you know this binomial distribution in this way. That's, or in our case, this would be if we have this drug and we know this is the probability of that it's effective, how many out of whatever 10 people, how many to get healed. But that's not really what we're interested in here, right? What we're interested in here is we have the data and we want to find the underlying parameter. So it's more like we observed 10 patients and we saw that 7 of them got healed. So what's the underlying what should this parameter be? And what we're looking at here is the likelihood. So this would be the probability of the observed data given this parameter. And of course, if we say, okay, 7 out of 10 get healed, then it's unsurprising that this parameter, this underlying probability, is somewhere around 0.7. And the spread of this distribution obviously will depend on our sample, how large our sample has been. Now, at the end of the day, that's not really what we want, right? We don't want here the probability of the observed data given our parameter, but rather we want to know what's the probability of the parameter given our data. So having this observation, what would be the probability that this underlying parameter is 0.7? Or in this case, of course, we have a continuous probability distribution, so we wouldn't ask, okay, what's the probability that this drug has an effectiveness of 0.7, 70% of people, but we would rather ask, for example, what's the probability that this effectiveness is greater than 70%, where we are integrating over our probability density. So we want to go from the likelihood, from the probability of data given parameter, to the probability of the parameter given the data. And of course, we use Bayes rule for this. If we want to use Bayes rule, we have to start off from a prior. And the prior we essentially just choose. We could say we don't have any idea about the effectiveness of this drug, so we make it equally likely that the drug doesn't work at all, or that it works in 100% of the people, or in 50%. So we could start with a uniform prior, or we could start off with saying, okay, we have a very high belief that it works, maybe because it's similar to another drug that works very well, or we have a belief that it actually doesn't work well, so we give a high probability to small values of the parameter theta. What I did in this case is I said, okay, our belief is that it will work in about half the people, so parameter somewhere around 0.5, but we don't have a very strong belief, so we don't put a lot of weight on the prior. What comes next is then the likelihood, so our observed data, the probability of those data given those parameters, and then we multiply prior times likelihood, and this is the posterior that we get. So what we're interested in, probability of the parameter given the data. And what you see is that our data have shifted this quite a bit towards our observed mean. It's not exactly the same, so it's still a bit further towards the lower values coming from the prior, but the data had quite a lot of influence here. And of course, this depends on the strength of your prior, how much weight you give to your prior, how many data you have, how much the posterior will actually get shifted towards the data or remain where it came from at the prior. But the important thing is usually the posterior. The posterior is between what the prior and your likelihood tells you. Okay, so far so good. So this is essentially what I believe you already know. So you know Bayes rule, you know how to apply Bayes rule, and now we want to come to this idea of this hierarchical model that I talked about. And again, to recap, we believe that this drug has a certain effectiveness in the overall population. And so I'm saying population, which maybe is not a very good idea talking about statistics. So what I mean here is not population as opposed to sample, but more in the sense of a biological population. So all the different kinds of individuals in this group, in this sample, no matter where they come from. If they come from the one group or the other group that we're looking at now. So we have this overall population, and we have some kind of parameter that describes the effectiveness of this drug. The overall population, but then we know that there are subgroups within this population, and these subgroups will modulate the way how this drug works. So the efficiency is still based on this overall parameter coming from the population, but it will differ a little bit in those groups. So again, we draw this parameter from the population, and then we will use a new distribution to describe the probability distribution within those two individual groups. So this one would be the allele A1, for example, and the allele A2. And this is why this is called hierarchical model, because we have this one hierarchy of the parameter that essentially that we choose from, giving us another parameter on which we then build the probability distribution on this lower hierarchy. Now you might say, okay, why do we want to do this? If they anyway, I mean, even if they're from subgroups, but essentially if we can also have a probability distribution for the complete population, why don't we just pool them all together and only use this pooled model? And the reason for this, of course, is because the variances, the variabilities within our subgroups may be smaller, and of course we want to describe our data as well as possible. So if we do have this additional information that gives us the opportunity to better describe somebody, if we know their genotype, then of course we will take that opportunity to have a better prediction of the drug efficiency for that person than if we wouldn't use that information. The other question is then, okay, but if we have now these groups that have these narrower distributions, these distributions with less variability, why don't we only use those ones and forget about that these came from different distributions? And the thing here is, of course, that even so the theoretical underlying distribution may have less variability for these subgroups, we may not actually have all this data, because obviously the sample that we take from a subgroup will always be smaller than the sample that we can take from the complete population. So taking this information from the complete population will help us in many cases to describe the sample better. So you could, for example, imagine that you have one sample where you looked at 95 patients of this maybe more frequent allele A2, and you only looked at 5 of the A1, then knowing that they come still from a common underlying distribution of this drug efficiency will help you to better estimate your first group. So if this first group, for example, was very different from the second group, then you might maybe still say, okay, we put our estimate still closer towards the other group, just because we don't have many data, so much data for this one group. On the other hand side, it could, of course, also be that you observe, okay, you have a lot of data for both groups, and they are actually quite different. Then you will say, okay, we do still put a lot of trust on this data, and maybe say, okay, our overall distribution probably has a wider spread than we have here. But the nice thing about those hierarchical models is they can incorporate all these cases and the cases in between. So you can have the situation where it's really helpful to inform your groups by the population, and also cases where you say, okay, we have a lot of data from the groups, so we don't need that so much. Okay, let's jump into this example. And we said again, okay, so we have our distributions for the individual groups that depend on this population parameter that we took. And then here, if, for example, say the population parameter for this group would be 0.65, then obviously we expect that our group parameter is distributed around this 0.65 somehow. Of course, we have to, this can be with different variances, so I chose a certain variance to depict this distribution. So now this is, of course, for a given value of this population parameter. However, this population parameter is a random variable. We don't know that yet. So what we can say here is we can say we describe a conditional probability, the probability of parameter theta 1 given the population parameter omega. So if you would have a very high omega, you expect that this distribution is far to the right, so there's a high mean of the zeta 1 distribution, or if omega would be very low, then you would have the distribution very far to the left, or if it's here in the middle, then well, you would also expect that in the group, the zeta 1 is somewhere peaking around intermediary values of around 0.5 or so. You do see that here there's a bit of a weird thing going on the edges, where it seems like we have very high probability, so very high conditional probability of theta 1 given omega, which essentially is just because, like here in the middle, the theta 1 can distribute towards lower and higher values, and here it's bounded, so it can only essentially distribute to the higher values, and that's why this looks or is a higher probability here. That's not super important for us. The important thing here is essentially just that the distribution of theta 1 depends on the omega, and this one here is, as I said, conditional probability. And we can also describe this, instead of this three-dimensional plot, we can also describe it as a contour plot, where we essentially project on the theta 1 omega axis, as you would do in a map. So you say, okay, our highest conditional probabilities are here in the middle. Okay, so far these are only conditional probabilities. Now, of course, we want to start off and say, okay, let's use a prior for our value of omega. That's similar as before. We can choose whatever represents our belief, and as before, I've chosen a case where we said, okay, we believe that in the population this drug is probably effective on about half of the people, and we don't put a very strong belief in this prior, so it's relatively broad prior. What I did here is I plotted it the other way around so that the omega actually is on the vertical axis and the probability associated with this omega is on the horizontal axis. The reason for this rotation you see here, because now we want to go from the conditional probability to our joint probability distribution, which essentially says, okay, for a given value of omega, we multiply by the probability of this omega here. And then if you do this for like essentially thinking about all these lines with different omega values, then you end up here at our joint probability distribution of theta 1 and omega. And now you see, because we have more prior weight, more probability in the prior, that we are at intermediary values of omega. Also our probability density distribution shifted, that we have the highest values here. So again, this is not a conditional probability anymore, but this is now a joint probability. So this would be or joint probability density. So we would say for both a value of theta 1 and omega being high, we expect, for both theta 1 being high and omega being small, we expect a small value. We don't believe that there's a low probability that the drug will work in the overall population, but a high probability that it will work in a group. And conversely, like high value of omega and small value of theta, so the group parameter, that's also unlikely. But then similar values where the population parameter and the group parameter essentially agree. This is something that we put higher trust on, and especially due to the prior that we said, okay, we believe that omega probably has an intermediary value. The probability densities around these intermediary values are the highest. And of course, this is now shown for theta 1, so this would be the 1 group, so for example, the one with allele A1. And we can, of course, do exactly the same procedure for theta 2, so for the one with the allele A2. And at this point, they would just look the same, just with different labels on our axis. Okay, at the point where they start being different is where we start putting data in. Okay, before that, very quickly, we can do the same thing also, just showing it as contours rather than as these 3D plots. Okay, so these ones are now our likelihoods. And I should say this example is actually based on an example from the book doing Bayesian data analysis from John Kruschke. And I actually took the same values that he has there. So in the book, they discussed it as an example where you have a factory that produces different coins, and then these coins have somewhat different biases, but still biases that come from the same factory. So they're probably similar, so they come from the same underlying distribution. And I took the same values simply to see if we can reproduce what's in the book there. And also we'll make a point based on these two values. So in the one group of patients, we looked at 15 patients, and we have 3 that are getting healed. And then if you look at this likelihood distribution, so that's the probability of the data given the parameters theta 1 and omega, we see that because only 3 of 15 got healed, this distribution is at low values of theta 1. For our other group, so this would be the group that has the allele A2, we have 5 patients and 4 of them get healed. So you can see that this distribution peaks at high values of theta 2. We can see that the distribution is wider because we have less samples. And you see that those distributions, so within each of the distributions, they are the same for different values of omega. So they are actually independent of omega. You can say the data are conditionally independent of omega if we condition on knowing, or if we condition on having a theta for which we describe those distributions. In this case, if those data are really like this, where you say, okay, in this one group we have this very low success rate, this very low efficiency, in the other one we have this very high efficiency, you might maybe go and actually question your model. Okay, do they actually come from the same underlying distribution, or is there something so fundamentally different about these groups that maybe it doesn't even make sense to say? We suppose that there is an underlying probability that describes the effectiveness of the drugs in both of these populations. But of course, in this case, these values were chosen deliberately to make a point further on. So we're going to stick with this model. An important point to point out is that in these plots, we are looking at marginal distributions. So in this case, we would have a likelihood that's marginalized over theta 2. So we're not showing or considering theta 2 in this plot. So you have to imagine that we are summing over the different possibilities of theta 2 in this case. And in this case, it's marginalized over theta 1. So we will be summing up over the different possibilities of theta 1 in this case. And similar for our priors, they were all also what's shown in these plots are actually the marginal distributions, not the full joint probabilities. So in the case of the prior, we would have needed the probability of theta 1, theta 2, and omega to fully describe the joint distribution, just as here we would need the probability of the data given theta 1, theta 2, and omega to fully describe it. But of course, then we get in a position where we would need 4 dimensions, and so it's getting difficult to show that. Okay, now we have our prior and our likelihood, and now we can go and calculate our posteriors. And so again, this one, the top one is the group 1, the bottom is the group 2, and then here this is the calculation of the posterior. So in this case, it's again a marginal posterior, but joined over the theta 1 omega parameters here, and over the theta 2 omega parameters here. What you see is that we still have this dependency. Obviously, if the population parameter gets higher, then also the, or let's say then the peak shifts also to higher theta 1s. And for a lower population parameter, we would also have the distribution of the theta at the lower end. The important thing to point out here is that this one is actually not simply multiplying each point of this prior with each point of this likelihood, exactly because we're looking at marginal distributions here. So this is something you can't simply do. Instead, these calculations are done for the complete joint probability distribution, and then again marginalized over, in this case, theta 2 or theta 1 here. You can see that it's not simply multiplying each point here with each point here in the case of the second group, because then you would expect that this peak is at higher values of theta 2 rather than so low. So instead, what we're seeing here is kind of that this peak is shifted to lower theta 2 values than we would have expected from our data. And we somehow have to assume that it is because of the influence of this other group, because they share this common population parameter, which is somehow pulling this peak towards the omega values that we're getting from this one here. And this one, I think, is something that's very hard to understand. That I had a lot of problems with. I'm still having problems with. Also because I'm somebody who likes to learn in this visual way. And here, of course, we have a problem because we essentially would need, as I said before, these 4 dimensions. So we want to describe a case where we have 2 parameters that are dependent on a common underlying parameter. So we would have 3 parameters, theta 1, theta 2, and omega. But then we also want to somehow describe, of course, the probability or the probability density associated with those, like here, where we had it on the z-axis. And then we would need 4 dimensions, and that's difficult to display. But still, somehow, yeah, what is it now that's pulling this peak? does it have to do with that we are just having, the same prior on both of them? You can already see from those selected values that this is probably not really the case, or that this is not the case, because this peak is actually pulled towards further to the left in terms of the theta 2 parameters than we would have expected it even from the prior. So based on our observed likelihood, we would have expected, a posterior that's quite towards high theta 2 values. So maybe something that's going along this diagonal but shifted a bit to the right. We see that this is not the case, but we see even that this is shifted towards the left, so towards smaller theta 2 values than even suggested by our priors. It's not just because we have a common prior that this peak is somehow pulled towards lower omega and therefore lower theta 2 parameters. But you might still wonder, okay, does it have to do with like incorporating this data maybe sequentially? Like, is it we're first incorporating the data from the group 1 and therefore let's say our prior changes or something like that, and we observe this. So this is something that's hard to get your head around, and in the following, that's my attempt to try to make sense of this, even though we only have a 3-dimensional space to plot in. Here is very quickly an illustration of, okay, this actually is not simply a multiplication of the prior and the likelihood, because if we were simply multiplying the prior and the likelihood, we would end up with a peak, which is here. Well, okay, in this case, theta 1, you could say, well, they don't look super different. However, in the case of theta 2, this is what we would get if we were simply multiplying those. This one is the actual posterior distribution. Again, the right way to do this is not simply multiplying the marginal prior and the marginal likelihood, but to go to the full joint probability distribution. And then once you have done the calculations there, you marginalize it. So yeah, let's try to somehow understand what this multiplication of the joint probability distributions means. And just to recap, our problem that we had was that essentially we have too many dimensions on which we would need to display something. So we have those two parameters, theta 1 and theta 2, which are both parameters that are dependent on another parameter, on omega. So we have 3 parameters, but now in addition, we would like to display also their probability. So we would have 4 things that we want to display. The way that I address this is via these plots. So in reality, what we would have is we have all continuous variables here. So essentially, this would be a space filled in a continuous fashion where everywhere you have a probability density. How this is often done for practical calculation is to divide the space into a fine grid. So you have points close together, usually regularly spaced, and at each point you assign a probability or a probability mass. What I did instead is I said, okay, each point in space, or every location, every continuous location in space would still have this probability, but now I'm sampling from this probability. So if there's a high probability, it's likely that I'm going to choose a point from it, or if there's low probability, then most likely I'm not choosing a point from it. So a high density of points essentially means a high probability density in this region. In addition, I did this color coding, so I'm not showing the legend here what exactly those values mean, but essentially the more you go towards yellow, the higher the probability density. So in this way, we can display 3 parameters and still via the density of points and by the color as well, we can show probability density for those parameters. I added those drop lines. I didn't add a drop line from every point, just to not make the plots too crowded. So these ones are also randomly selected. And again, if we now project this onto one of those walls, so for example, if we project it onto the wall of theta 1 versus omega here, then we would get this plot here. So this is the marginalized probability, marginalized probability density for theta 1 versus omega, in this case marginalized over theta 2. Okay, now we need to go back to our likelihood for the data, and I didn't go through this in detail how this was calculated before, but now since we really want to make sure that we have the likelihood over this joint distribution of our parameters, let's look at it in a bit more of detail. So the probability of the data given this joint distribution of all three of our parameters. So theta 1 and theta 2 for sure are not independent. However, they are independent given omega. So once we know omega, then knowing theta 2 won't tell us anything more about theta 1. If we wouldn't consider omega, it would, but if we consider omega, if we know omega, then this is not the case. And the same the other way around. Once we know omega, then knowing theta 1 won't tell us more about theta 2, because essentially omega already tells us everything. So we have this case of conditional independence. So we can split up this probability of the data given theta 1 and omega times probability of the data given theta 2 and omega. Having done this split, we can now also say, okay, the data are independent of omega once we know theta 1. So if we have our theta 1 given, then knowing omega won't tell us anything more about the data. In the same way for theta 2. So again, we can actually drop this omega because the data are independent from omega. So we now simply have probability of data given theta 1 times probability of data given theta 2. And finally, we remember back that we had these two data sets from where we knew that one of them comes from our patient group that had this allele A1, and the other one came from the patient group that had the allele A2. So obviously the one that has allele A2, the data 2, they are not going to be dependent on the parameter for the other group, and vice versa, the ones that come from group 1, they won't be dependent on the parameter of group 2. So we can also split our data here into this one part of the data set coming from group 1, which depends on parameter 1, and the other part coming from group 2, which depends on the parameter of group 2. So now we have a way of calculating our factorized likelihood via, in this case, a binomial distribution. So what's the probability of getting a certain number of observations given, a certain number of, let's call them successes or whatever, or a certain number of healed patients out of a given number of observations of patients that we looked at. And this likelihood is shown here. So the idea for the plot is the same as before, showing these three parameters and showing the density of the points in this region. And what we can see here is that we have essentially this cylinder here of data where we have this high density. This cylinder where we have low values of theta 1, because we remember that not many of the patients in this group 1 got healed, and on the other hand side, rather high values for theta 2, because many of those patients got healed. Again, we see theta 1 and theta 2 are not independent, but once we look at both of them, so once we look at the joint distribution of both of them, they are independent of omega. So for each value of omega, essentially, we will have the same picture. So every slice will give us the same picture for those two parameters. Again, we have this cylinder. If we look a bit more closely, it's not exactly a cylinder. It's actually a cylinder that's stretched a bit, also incorporating lower values of theta 2, versus in the theta 1 direction, it's pretty narrow. And this reflects that we had quite a lot of data for group 1, but not so many data of group 2. So it's spread out a bit more here. So now we're really looking at these joint probability distributions of all of our parameters. And that means we can actually calculate the probability at each point in the prior with each point, with corresponding point in the likelihood. So if we had a place where we have a very high density in the prior and a very high density in the likelihood, we would get a very high density in the posterior. If we have a very low density in the prior and very low in the likelihood, we would get a very low in the posterior. So what do we have? So we have this region, this cylinder, where we have very high values, but we see that essentially our prior is saying, no, there isn't any or almost no density in the prior, because the prior says we do not accept this disagreement between parameter θ1 and θ2. Instead, because θ1 is closely related to omega and θ2 is closely related to omega, this essentially also means that θ1 and θ2 need to agree, so these data aren't really possible. The only way how we can get not necessarily a very high, but at least a decent, relatively high posterior density is if we multiply points in the prior that are high with points here that are not very high, but at least have some kind of probability. So the ones where we have θ1 being high and θ2 going more in the lower region again, because only we need to have points where we have agreement between those two. Then we would also have low values for omega in this case. For θ1, we don't have much wiggle room again because we have pretty strong data. So θ1 is pretty much set on where it thinks this distribution should be. θ2, we don't have so many data, so there is room for uncertainty, so this is possible. So it's essentially the θ1 data which largely determine where our posterior is going to be. And then if we look at that, we see exactly in the posterior we are in a region that comes from where the prior was high, so we have a good agreement between those two, but which is pulled towards lower values because θ1 is pulling it to these low values. And then essentially θ2 doesn't have enough data, let's say, to resist this pulling. And so we see that we're in this part here. And now we understand what it means that the θ2 is getting pulled by θ1. Essentially, that we need to take a part out of the prior that is allowed by our prior distribution. And again, in the prior, there was not this direct association. The prior didn't directly say, okay, θ1 and θ2 need to be associated or agreeing, but they indirectly need to agree because they're both related to omega in the same way. So what we can do is now, again, marginalize our posterior over one of the parameters. So here you need to flip this in your head now and make sure that you understand what is on which axis. But so this one would be θ1 versus omega versus the probability of this joint θ1 omega marginalized over θ2. And you see we're at both low values here. And then the same idea marginalized over θ1. And you see, okay, we're always where we have this agreement between the parameters. So either low values of both parameters or high values of both parameters. θ1 is the one which is determining, okay, it needs to be at low values. Our data say it is at low values of θ1, therefore it needs to be at lower values of omega. And now since we know that it's at lower values for omega, it also needs to be at lower values for θ2. So we understand why we saw in the marginalized posterior what we saw before, having looked at those joint probability distributions. So finally, we can ask what happens if we actually only acquire data from one group. So is our belief about the distribution of the data of group 2 going to be changed if we only add data or only add observations for group 1? And the answer is yes, it is. So again, this one was our prior as before. So with this strong relationship of θ1 and θ2 via the underlying population parameter omega. And then these are the data that we observe. So what we say here is we get data for theta 1 that suggests that theta 1 should be low, so somewhere around here, 0.2, 0.3. But then we have this spreading out of theta 2, which simply comes from the fact that we didn't make any observation, didn't make any measurement on theta 2. So there is no opinion of those data where it should be. And then we can simply say, okay, if we multiply this, then we have from the prior a contribution that says, okay, low values of theta 1 should be associated with low values of omega, high values of theta 1 should be associated with high values of omega. And because now we have low values of theta 1 here, meaning we need to be associated with low values of omega, but then at the same time, low values of omega also mean low values of theta 2. We do actually get a selection and a change in the belief about theta 2 as well. So what we end up here is, again, we're in this corner at low values of all three of the parameters, even more strongly than before, because theta 2 is not doing anything to contradict this. So it's essentially just the theta 1, which is saying, okay, we should be here, or more strictly, theta 1 is saying, okay, we should be here at a low value. The prior is saying, okay, if low value of theta 1, then this needs to be associated with a low value of omega, so we need to be in this corner, and then consequently, this is setting that theta 2 is also in this lower corner, essentially because theta 2 didn't utter any opinion. And if we look at the marginal distributions, we see the same thing. So this one would be theta 1 versus omega. Since our data told us, okay, theta 1 should be low, and we need to have this correlation between theta 1 and omega, we are in this corner here. And then because those data said, okay, omega should be low, this tells us then the theta 2, which didn't by itself, contain any vote where it should be, it's going to be forced also in this corner, and or corner of low values of both parameters. And then finally, if we look of theta 1 versus theta 2, then this leads us exactly to this picture, that essentially our observation on theta 1 necessitated that also theta 2 is at low values, or has a high probability to be at low values. So let's ask one more question. Let's go back to the previous case where we observed data on both the group A1 and the group A2. And let's ask what is going to happen if we observe these data repeatedly. So again and again and again. So the situation where we already were before, we said we have our prior, we observe data, we calculate the posterior, and we saw that we get the probability density, the joint probability density in the posterior, moving towards essentially where the likelihood wants it to move, or where the likelihood tells it to move, so towards this upper right corner. And we said, okay, we have more data on theta 1, so theta 1 is having a stronger influence. And now what we're just doing is we're adding repeatedly those same data. So in practice, of course, it's unlikely that you would be observing exactly the same data, but just for the sake of demonstration, we'll say, okay, we'll actually observe exactly the same numbers over and over again. And then you see, okay, you don't see much of a difference if we just go to round 2. So let's actually go a bit further. So what's shown here is we have our prior, then this one will be after 5 rounds, 10 rounds, 15 rounds. And what you see is that once we get to 30 rounds, 50 rounds, now our distribution really is overwhelmed by the likelihood where the data tell it to be. So eventually, just like in our regular 1 or 2 dimensional case, we also see here that data can overwhelm our prior. And in this case, the prior has 2 kinds of information. There was on the one hand side this strong relationship between the parameters, both of the theta parameters of the lower level depend in the same way on omega. And then there was also this information that our prior on omega had a higher density at those intermediate values of omega, which is a bit harder to recognize here. But just as a prior, also in those simpler cases, can be overwhelmed by data, it has also been overwhelmed here after adding quite a lot of data again and again. And of course, we can encode that in the prior, how much of a prior we believe we have. And that also means we encode how much do we actually believe that those two samples come from a group that should behave similarly. So, for example, that should have the same mean or the same median. So here we're just looking at the marginalized distributions of what you just saw before. So up here we would have the theta 1 distribution, the theta 2 distributions, and then the omega distributions, and here increasing number of rounds where new data is added. You can see here, this is the first round and the third and only up to the fifth one here. And you see that the highest densities for those parameters are moving towards where we had the mode of the likelihood. So these blue lines indicate the mode of the marginalized likelihood for these parameters. And you see that the parameters are moving towards this line. Theta 1 faster, because again, we have more data than this, than theta 2. But eventually also theta 2 will get pretty close there. Here on the right, this is just showing the same thing. If we weren't adding over essentially what is 5 steps here, so 5 rounds here, this data, but if we only added in a single step the 5 times higher number of data at once, then we arrive at the same picture here. And finally, this plot is showing the development of the parameters just over the rounds of adding more and more data. And again, in this case, I'm just adding the same data over and over again. And we're going up to 100 rounds. And what you see again, the parameters are going close to where there is the mode of the likelihood. Theta 1 reaches it around here, I would say 50 rounds or so. Theta 2 still hasn't completely reached it even after 100 rounds, so this is taking much longer. We see in the beginning something a bit interesting, that theta 1 is pulled very close to the theta 1 estimate, and then only with increasingly adding more and more data, it pulls the posterior towards where the data tell it to go. So I hope this has been useful. Looking at the distributions of these hierarchical models essentially in 4 dimensions. These hierarchical models essentially, the simplest ones start from 3 parameters or more, so we need this bit more complex way of visualizing. And then, as I said, if you have some intuition or something visual to refer to, then it's hopefully easier to understand also hierarchical models, even if those ones are then completely impossible to plot the complete joint distributions, and you do have to refer to the marginal distributions.